Hello there. I'm glad you've slipped into this little pocket of quiet with me tonight. Outside, the universe goes on in its vast, familiar way. Stars turning, galaxies drifting. But together, we're going to lean in the opposite direction. Not out toward the distant, but down toward the unimaginably small. There is a scale where our usual ideas about distance and size start to crumble, where space itself seems to flicker and blur, and the smooth fabric of reality begins to look more like a restless sea. Tonight, we'll wander gently into that hidden territory, the tiniest steps nature will let us take, and what might truly be happening there when no one is looking. If these soft, curious journeys keep you company in the dark, a simple like and a quiet subscribe help others find their way here too. No hurry. When you're ready, we'll begin. You can imagine it as a slow, patient zoom, not the quick pinch of fingers on a screen, but a quiet drift inward. First, the familiar things fall away. The lines on your hand, the texture of fabric, the tiny grains of dust in the air. What looked smooth begins to show structure. Skin becomes a landscape of cells. The air becomes a soft swarm of molecules. It feels as though, if you just keep going, the universe will go on revealing itself. For a long time, that was the quiet hope inside physics, that there would always be another layer waiting if we built a better way of seeing. If we could shrink our gaze past atoms, past the nuclei inside them, past the quarks inside those, perhaps there would still be finer details, new secrets. The question seems simple. If you never stop zooming in, does nature never stop giving you more to see? Or, at some point, does the picture itself begin to fall apart? Every attempt to answer that question has followed the same gentle rule. Even if the machines have been anything but gentle, to see smaller, you need more energy. It is like trying to trace a pattern on dark fabric. You need a light with a finer, sharper beam. The light that our eyes know, the soft rainbow from red to violet, comes in waves that are simply too wide. Each wave is hundreds of nanometers across, roughly 1,000 times larger than an atom. With waves that big, the atom is like a pebble hidden under a wide blanket. No matter how good your glass lenses are, they cannot show you what is smaller than the waves they use. So scientists learned to trade light for something else. Electrons, the tiny charges that run through every wire and every living cell, also have a wave side. Their waves can be made much shorter if you give them more energy, pushing them to higher and higher speeds. In the early 20th century, a quiet revolution began in the laboratories. Glass lenses were joined by magnetic ones. Instead of bending light, they curved the paths of electrons, bringing their tight, small waves into focus. In 1931, a German physicist named Ernst Ruska built the first electron microscope. With electrons as his light, he could step past the barrier that ordinary optics had drawn. The world that opened up was both familiar and strange. Cells, once vague shapes, revealed inner scaffolds and organelles. Crystals showed repeating patterns. Even individual molecules, once only symbols in chemistry books, gained outlines and presence. As the decades passed, the same rule, shorter waves, higher energy, finer detail, kept guiding us deeper. At the Stanford Linear Accelerator Center in California, long tunnels were built to give electrons enormous energies. Instead of using them to make images, scientists flung them directly at protons, the positively charged particles inside atomic nuclei, and watched how the electrons scattered. What they found changed the story of matter. The proton did not behave like a solid, simple bead. Its scattering pattern whispered of structure within, of smaller pieces jostling inside. From those measurements grew a new picture. Protons are made of quarks, held together by gluons, a restless, buzzing community, rather than a single, quiet point. The experiment earned a long, serious name: deep, inelastic scattering. But the heart of it was simple. Once again, by using more energy, we had peeled back another layer. From there, a kind of map emerged. If you want to see inside atoms, you need a certain scale of energy. To probe the nucleus, you need far more. To look inside protons and neutrons, more still. Each leap downward in size demands a leap upward in how fiercely you disturb the system. Wanting to see what lies below quarks means imagining energies that strain the limits of what we can even picture. Hidden inside this path is a trap, though one that does not come from technology, but from nature itself. The more you try to focus your energy into a tiny region of space, the more you start to change the very stage on which everything takes place. According to Einstein, energy and mass are simply different ways of talking about the same thing, and mass, wherever it gathers, bends space-time. At first, when you pack energy into a small area to probe tiny distances, the bending is gentle, like a slight sag in a stretched sheet. The particles still move, more or less, as you expect. But as you imagine concentrating more and more energy into an ever smaller region, the sag deepens, the sheet curves, then droops, then begins to form a well. Push the idea far enough, and something dramatic happens. The energy you have crammed into that minuscule spot creates so much gravity that it can no longer support itself. It collapses, pulling in on itself, wrapping space-time so tightly that an invisible boundary forms. On one side of that boundary, signals can still escape. On the other, nothing. Not light, not particles, not information, can climb back out. In trying to look more closely, your microscope has made a tiny black hole. That is the universe's quiet way of saying no further to that method. Add more energy, and you do not see smaller details. You simply deepen the trap. Any attempt to sharpen your probe beyond a certain point only makes the horizon tighter and the darkness more complete. The very trick that brought us from cells to molecules to quarks suddenly turns on us and draws a curtain. Physicists can write down the scale at which this begins to happen, a length so small it stretches the imagination until it feels almost meaningless. It is called the Planck length. In meters, it is about 1.6 times 10 to the minus 35, a 1 with 35 zeros after the decimal point before you reach the first digit. One way to feel its smallness is to play a thought game. Enlarge a proton until it is as big as the Earth. On that enormous proton planet, the Planck length would still be smaller than a single atom in a grain of sand. As unreachable as it seems, the Planck length is not just a mathematical curiosity. It marks a border in our understanding. According to our best theories, if you try to focus on distances shorter than that, you run into a storm in the fabric of space-time itself. The smooth stage you have been imagining, with lines and neat grids, starts to tremble. Space and time no longer behave like a calm, continuous sheet. They jitter and foam, like water simmering just before a boil. The physicist John Wheeler gave this restless picture a name: quantum foam. In that regime, tiny, fleeting distortions of geometry are thought to pop in and out of existence. Curved pockets of space-time swell and collapse. Little tunnels and bubbles may flicker at scales so small they can barely be called places at all. The comfortable ideas of here and there, of a clear path from one event to the next, begin to lose their grip. To truly reach that realm with an experiment, we would need energies so extreme that even our boldest machines fall silent, about 10 to the 19th power in giga-electron volts. Compared to that, the Large Hadron Collider beneath the French-Swiss border is like a gentle whisper. Even if we wrapped a particle accelerator all the way around our galaxy, the goal would still slip through our fingers. So the Planck length behaves like a kind of universal border, not a hard wall in space, but a limit to how finely reality can be measured using the tools we know. Below that scale, the very notions of length and time interval start to blur. It is as if the universe is telling us that asking for a smaller tick on the cosmic ruler stops making sense after a point. Physicists are drawn to this boundary because it is where two great descriptions of nature meet and struggle: quantum mechanics, which handles the jitter of particles, and general relativity, which describes the smooth bending of space-time. Both work beautifully in their own domains, but at the Planck scale, their languages clash. Somewhere in that argument, many believe, lies a deeper, quieter theory that will hold both gravity and quantum behavior in a single frame. When we look outward with a telescope like NASA's James Webb, we use light's long journey to peer back in time, catching the glow of galaxies as they were more than 13 billion years ago. Turning inward toward smaller and smaller structures is another way of traveling in time. Each layer we peel back in matter echoes an earlier chapter of the universe's own story. The energies that bind nuclei together recall the first brief seconds after the Big Bang. The dance of quarks and gluons reflects the first sliver of a microsecond after everything began. Carry that idea all the way down, and the Planck length sits at the very first heartbeat of space-time itself, the moment when distances and durations first became meaningful. To ask what lies below, that is to ask what it means for before to exist when time has only just emerged. So the question that began as a simple, childlike curiosity, can we just keep zooming in forever, slowly turns into something deeper. If you could somehow look beyond the Planck scale, would you find a wild, chaotic froth with no pattern at all, or an even more delicate order, one that our present mathematics cannot yet describe? For now, the Planck length remains both a stopping point and a signpost. It is the place where our instruments, our equations, and our imaginations all begin to strain at once. Beyond it, the universe offers no clear picture, only a thoughtful silence. It is as if the laws we know draw a soft horizon and then fall quiet, inviting us to wonder what kind of language might be needed to speak of what lies past that line. And in that quiet, another thought begins to form. If light itself cannot guide us further into this tiny, trembling frontier, perhaps there is some other way to listen to what the smallest scales of nature are trying to say. One of the first clues toward that other way of listening comes from a question that sounds almost childlike in its simplicity. If light is how we see the world, why does it fail us when we try to see the tiniest pieces of it? We are used to thinking of light as a perfect messenger. Every sunrise, every photograph, every memory of a familiar face comes wrapped in it. Light brings us the shimmer of oceans and the glow of distant galaxies. It feels natural to imagine that, if we had strong enough lenses and clever enough microscopes, light should be able to show us anything at all, right down to the smallest building blocks of matter. And yet, when scientists tried to use ordinary light, to peer directly at atoms. The atoms did not appear. No amount of polishing the glass helped. The failure was not in the lenses or in the hands that built them. It was in the way light itself behaves. Every ray of light, for all its brightness, is also a wave. Waves have a size to them, a length from one crest to the next, and a wave cannot faithfully reveal details much smaller than that length. If the thing you are trying to see is tiny compared to the wave that probes it, the wave simply glides over the fine structure, smoothing it out. The colors our eyes know best, from deep red to violet, all have wavelengths clustered around a similar scale. Each wave of visible light is hundreds of nanometers long, while an atom is closer to a fraction of a nanometer across. It is as if you are trying to read the tiniest handwriting at the bottom of a page, but the ink lines you draw to trace it are thicker than the letters themselves. The subtle curves and corners are lost inside the stroke. So when you shine ordinary light on atoms, the light does interact with them. It scatters, it is absorbed and re-emitted, but it cannot separate one atom's outline from another with any clarity. The ripples are simply too broad. The atom is there, but for visible light it might as well be a whisper beneath a crashing wave. The natural thought, then, is simple. If the ripples are too large, make them smaller. Use light with shorter wavelengths. Slide up the spectrum to more energetic colors, into ultraviolet, then farther still into X-rays, where each crest and trough is squeezed closer together. Shorter waves should be able to slip between atoms, tracing their positions, picking out their patterns. And, in a way, that does work. With X-rays, scientists learn to read the arrangements of atoms inside crystals. By shining these higher energy photons through an orderly grid of atoms and studying the pattern in which the rays spread out afterward, they could reconstruct the underlying structure. It was like casting a shadow, not of a solid object, but of the invisible scaffold inside a piece of matter. Those early X-ray experiments revealed that atoms in a crystal do not sit randomly. They arrange themselves in neat, repeating lattices, like a vast, three-dimensional wallpaper. From those repeating patterns came our first clear sense that the atomic world had geometry, not just chaos. But when light is pushed to that energy, it gains a harsher side. A photon, energetic enough to match the scale of an atom, carries far more punch than the soft light of a candle flame or the sunlight on your hand. It can knock electrons free, tear atoms apart, and reshape the very structure it is meant to reveal. You can still learn from what happens, but it is like inspecting a snowflake by firing tiny bullets at it. The pattern you see is mixed with the damage you cause. That is where another actor steps quietly onto the stage, the electron. It is not light, it is matter itself, one of the particles that make up atoms. Yet, at the quantum level, it also has a wave side. In the 1920 seconds, a young physicist suggested something almost unsettling in its simplicity. Anything that moves has a wavelength. Not just light, but particles too. The faster they move, the shorter their associated wave becomes. This idea that matter carries its own wave sounded strange at first, even to experts. Particles were supposed to be tiny bullets of stuff, not rippling patterns. But then, an experiment brought the idea into focus. A thin crystal of nickel was placed in the path of a beam of electrons. Instead of simply bouncing off like little marbles, the electrons produced a delicate pattern of bright and dark bands, like the interference fringes you see when waves overlap. Only waves make patterns like that. The electrons, for a moment, had behaved as if they were light, That image was a turning point. It showed that electrons could be coaxed into acting like waves with very short wavelengths, just the right size to explore the spacing between atoms. And because those electrons needed only modest amounts of energy to reach those wavelengths, they could probe matter with a much gentler touch than harsh, high-energy X-rays. From there, the electron microscope was born. Instead of glass lenses, coils of wire and magnets guided and focused beams of electrons. Instead of visible light reflecting off a surface, there were streams of charged particles, their waves bending and scattering as they passed through thin slices of material. Detectors captured those changes and turned them into images. Under these new eyes, a hidden world unfolded. Structures that had once been pure theory, membranes enclosing cells, the shapes of viruses, the arrangement of atoms in a solid, gained outlines. They were not painted with light, but with the quiet rippling of matter itself. The beauty of this approach lies in the balance it strikes. To make light see on the scale of atoms, you must push photons to energies so high that they start to scorch and tear the scene you are trying to study. To give electrons similar resolution, you need far less energy. An electron with only a few hundred units of energy in the quantum scale has a wavelength naturally suited to the spacing between atoms. It can feel the structure without instantly destroying it. Seen side by side, the difference feels almost unfair. Light, the grand storyteller of the cosmos, must work so hard and burn so hot to glimpse an atom that it risks erasing the story entirely. Electrons, the quiet workers inside every atom, can reveal the same details with a softer touch. In modern laboratories, when someone wants to map the positions of atoms on a surface or see the skeleton of a molecule, they rarely reach for light at all. They reach for electrons. They tune their beams with magnets, sweep them across samples with astonishing precision, and let the subtle interference of matter waves paint a picture. The images that result are not photographs in the ordinary sense. They are maps of probability and interaction, built from how those electron waves are altered as they pass through or bounce from the sample. Still, when assembled, they look uncannily like what we would call a picture. Dots arranged in rows, lines marking boundaries, delicate patterns that reveal where atoms sit, how they line up, how they bind. The finest of these instruments can resolve distances smaller than the diameter of a single hydrogen atom. At that scale, what you see is not a solid bead, but a cloud of presence, a place where the electron around a nucleus is most likely to be found. The very idea of a crisp, tiny ball begins to give way to something softer and more spread out. Underneath all of this is a simple rule that threads through everything. Shorter waves can reveal finer details. Make your wave smaller, and the universe offers you smaller patterns. But that rule comes with a cost, one we felt in the previous reflections. Shorter wavelength almost always means higher energy, whether the wave belongs to light or to matter. And if you keep driving that energy higher and higher, trying to sharpen your view without end, eventually you do not just disturb the thing you are looking at, you disturb space-time itself. That is why electron microscopes sit in a kind of sweet spot. They use matter waves that are short enough to pick out atoms, but not so energetic that they tear everything apart. They live in a middle ground between gentleness and power, where we can see deeply without collapsing what we are trying to understand. The same balance shows up in other corners of our curiosity. Out in space, telescopes like James Webb choose to look in infrared with waves longer than visible light. Those waves do not reveal smaller structures. They reveal fainter ones. They slip through dust, catch the glow of cool, distant objects, and show us galaxies forming in the early universe. On Earth, by contrast, particle physicists build machines that use waves unimaginably short, energies staggeringly high, all to nudge matter and see if there is anything smaller, any deeper layer beneath the particles we know, between the long, soft waves that listen for faint echoes in space and the fierce, tiny waves that shake particles apart in accelerators. There is a continuous spectrum of ways to see. Light and electrons are just two different guides along that spectrum. Light tells us how the universe appears from the outside, its colors, its shapes, its motions across the sky. Electrons tell us how the universe is assembled from within, its hidden scaffold of atoms and bonds, the quiet architecture that holds everything up. Looking back, it is almost astonishing how strange this realization once seemed. When those first electron diffraction patterns appeared, many of the scientists involved hesitated. Electrons were supposed to be little chunks of charge, not delicate waves, but the patterns on the screens and plates were clear, rows of bright and dark bands that matched what waves produce when they interfere. In that moment, the clean line we like to draw between what we look with and what things are made of began to blur. Light, once thought of as pure wave, had already revealed its particle side in other experiments. Now, particles of matter were showing their wave side. The two categories, light and stuff, no longer felt as separate as our everyday experience suggests. Later, one of the great explainers of physics would point to this dual nature, the way electrons and photons are both waves and particles, and call it the central puzzle of the quantum world. If you try to force nature into the boxes of classical thinking, it slips out. At very small scales, it insists on behaving in ways that do not fit neatly into the pictures we inherited from our larger, slower lives. Yet from that strangeness, something quietly beautiful emerges. When we tried to use light to see matter, we discovered that matter itself carries a kind of light within it, a wave, a rhythm tied to its motion. By listening to that rhythm, instead of forcing our familiar light into places it does not easily go, we learn to see structures that had been forever hidden from our eyes. So when we say that electrons can see atoms while light cannot, what we really mean is this. At the scale of atoms, nature invites us to use matter to reveal matter. The patterns we seek appear most clearly when the probe and the thing probed share the same quantum language. Electrons, with their gentle, tunable waves, speak that language fluently. And as we follow their guidance deeper, resolving atoms and then noticing that even they are not featureless, another question begins to glow at the edge of awareness. If atoms have structure, built from electrons orbiting around a concentrated center, what about that center itself? The protons and neutrons in the nucleus, are they the end of the story? Or do they, too, hide smaller patterns waiting quietly to be found? You can almost feel the question waiting inside the last one. If atoms have structure, with electrons spread out in soft clouds around a concentrated center, what about that center itself? The tiny heart we call the nucleus. Is it truly solid, like a marble at the core of emptiness? Or, if you could somehow look inside, would it open up into yet another world? For a long time, physicists pictured the nucleus as the final, dense core of matter. Protons and neutrons were treated like tough little bricks, packed tightly together, holding almost all of an atom's mass. The rest was mostly emptiness, with electrons wandering in the surrounding space. That picture came from a simple but brilliant experiment in the early 1900s, when Ernest Rutherford and his colleagues aimed a beam of fast-moving particles at a sheet of thin gold. Most of those particles passed straight through the metal as if it were almost nothing, but every now and then, one bounced sharply back. From that strange behavior, Rutherford inferred that the atom could not be a soft, uniform blob. Almost all of its mass had to be concentrated in a tiny central region, with the rest of the atom spread out thinly around it. The nucleus was like a speck inside a cathedral, occupying a space far smaller than the building it defined. That discovery itself was shocking. It showed that what feels solid to us is mostly space, held together by forces we cannot see. But as the decades passed, the curiosity that had already peeled away so much could not rest. If the atom was not smooth, why should the proton and neutron be? Was the nucleus truly the final, indivisible heart, or just another stage on the way down? To ask that question seriously, scientists needed a more delicate tool than the one Rutherford had used. His alpha particles were relatively large and clumsy as probes go, more like pebbles than needles. They could reveal that the nucleus existed, but not whether it had fine structure. To go deeper, you would need to hit the proton with something sharper, point-like, and incredibly energetic, something that could graze its interior and come back bearing news. That something turned out to be the electron. As far as we can tell, electrons have no size at all in the conventional sense. They behave as if they are point-like, with no inner parts. That makes them almost perfect messengers. When a fast electron approaches a proton and deflects, the way it bounces carries information about the charge and structure it has encountered, not about itself. In the 1,960 seconds, a place was built specifically to send such messengers on their way, a long, straight accelerator in California, known as the Stanford Linear Accelerator Center. Underground, a narrow tunnel stretched for kilometers, quietly pushing electrons closer and closer to the speed of light. By the time they emerged, each electron carried an enormous amount of energy in its motion, and with it, a very short associated wavelength, just what was needed to probe deep inside the proton. The idea guiding the experiments there was simple, but bold. Aim these high-energy electrons at the protons and neutrons bound inside atomic nuclei. Let them collide. Then watch, with great patience, where the scattered electrons go. If the proton were a smooth, solid ball of charge, the scattering angles would arrange themselves in a pattern we could predict. If there were smaller, harder bits inside, the pattern would change. Some electrons would ricochet as though they had struck tiny, concentrated spots, like pebbles hitting hidden nails in a wall. The collisions they studied were not gentle. They were called deep inelastic, a quiet phrase for interactions violent enough to shake the proton apart and redistribute its energy. In such events, the electron does not simply graze the outer surface. It plunges inward, exchanging energy with the proton's interior, and the fragments and spray that result are recorded. When the first data began to accumulate, around 1,968, the results did not match the vision of a solid, featureless sphere. Instead, certain electrons scattered sharply, as if they had struck small, resistant cores inside the proton. The pattern suggested three main concentrations of charge, three stubborn points that kicked back most strongly. Those 3 points matched an idea that, until then, had lived only in equations and speculation. A few years earlier, theorists like Murray Gell-Mann and George Zweig had suggested that protons and neutrons might be made from even smaller constituents. They had given these imagined particles a curious name, quarks. The word itself came from a line in a novel, playful and strange. a reminder that no one had actually seen such things. They were convenient building blocks in a mathematical scheme, nothing more. But the scattering patterns from those high-energy electrons seemed to say otherwise. The data whispered that inside every proton were 3 smaller bundles of charge and momentum, behaving during very short, very energetic encounters, almost like free particles. Suddenly, the quark was no longer just a clever bookkeeping trick. It began to look like something real. From that point, the picture of the nucleus changed again. Protons and neutrons were no longer indivisible beads, but composite objects. Each contained 3 quarks held together by a powerful interaction, the strong nuclear force. To describe that force in detail, another theory took shape: quantum chromodynamics, or QCD, with quarks carrying color charge and exchanging particles called gluons. Despite the colorful names, the essence is simple. Quarks are never alone. The gluons that bind them are not just passive threads. They interact with one another and constantly create and destroy quark-antiquark pairs. If you could somehow freeze time and peer into a proton, you would not see 3 marbles sitting quietly. You would see a seething storm of activity, quarks darting and colliding, gluons flickering in and out, pairs of particles emerging and vanishing, all woven together so tightly that the proton, from the outside, behaves as a single, stable entity. One of the most surprising features of the strong force is how it changes with distance. At very short separations, the kind you probe with extremely high-energy electrons, quarks, behave as if they are almost free, gliding more or less independently. This property is called asymptotic freedom. The closer you look, the less tightly they appear to be bound. But as you try to separate them over larger distances, the force between them grows instead of weakening. It is as though the more you pull, the stronger the restoring pull becomes, like stretching a rubber band that refuses to snap. Pull hard enough, and something remarkable happens. Instead of a single quark breaking away, the energy you pour into the system turns into new quark-antiquark pairs. The band does not break. It simply creates additional links. That is why no one has ever isolated a lone quark in the lab. Any attempt to tear one free only produces more bound combinations. Quarks remain forever confined inside particles such as protons and neutrons, grouped in 2s and 3s and more, but never seen wandering alone. This confinement, frustrating as it is for our desire to hold and inspect the basic pieces of matter, is also what makes the world stable. The strong force is intense enough and persistent enough to hold protons together for times longer than the current age of the universe. It binds nuclei so securely that atoms can exist, stars can fuse hydrogen into heavier elements, and structures from dust grains to living bodies can endure. The distances involved in these experiments are almost unimaginably small. The energies used at places like Stanford, CERN, and Fermilab correspond to probing lengths on the order of a quadrillionth of a meter, far smaller than atoms, far smaller even than the nucleus itself. At that scale, the familiar division between solid and empty begins to lose its meaning. A proton, which we might once have imagined as a tiny billiard ball, becomes instead a swirling cloud of fields and probabilities, with most of its apparent mass coming not from the bare quarks themselves, but from the energy of their motion and their binding. In that sense, matter is even more subtle than mostly empty space. It is mostly energy, folded into patterns by quantum rules. What feels heavy and solid at our scale is, on its deepest level, a kind of ongoing dance. The way we learned this was not by opening protons like walnuts, but by scattering. Over and over, physicists have thrown particles at particles and watched how they recoil, like listening to the echoes of a bell struck in the dark. From those echoes, the angles of deflection, the energies of the fragments, they have inferred the shape of what rings. The experiments at Stanford were just the beginning. Later, circular accelerators at CERN in Europe and Fermilab in the United States hurled protons against protons and protons against antiprotons at ever-increasing energies. These collisions created showers of particles whose patterns confirmed and refined the quark picture. They revealed how quarks share momentum inside a proton, how gluons carry a large fraction of its energy, how the sea of temporary pairs contributes to its behavior. Again and again, measurements of how particles scatter have matched the predictions of quantum chromodynamics with astonishing precision. The theory's peculiar features, asymptotic freedom at short distances, confinement at large, have held up. The nucleus is not a solid ball of stuff. It is a region where quark and gluon fields are tightly knotted, a tiny storm whose average behavior gives rise to the stable objects we know. And yet, even this picture may not be the final word. Some physicists have wondered whether quarks themselves might be composite, built from even more fundamental entities, sometimes given names like prions. So far, though, every attempt to find signs of deeper structure has come up empty. The energies required to test those ideas directly would be far beyond what we can generate now, pushing us closer to the limits where our very notions of space-time begin to warp. The frontier continues to move. Modern accelerators now reach energies in the trillions of electron volts, smashing protons together so violently that for an instant, the conditions resemble those of the early universe. In the sprays of particles that emerge, researchers search for any deviation from the patterns they expect, any hint that, beneath the quark and gluon sea, something stranger is stirring. So far, the quark model and the strong force have held their ground, but the questions grow alongside the machines. If we keep raising the energy, keep narrowing our focus, will we simply find more of the same swirling storm inside protons? Or will some new layer finally show itself? A fresh structure, a different kind of order, hinting that even the quark is just one more step along a path that has not yet reached its end. For now, the picture we have is already rich. The atomic nucleus is not hollow in any simple sense, but it is not solid either. It is a place where the most intense forces we know bind restless, point-like quarks into stable wholes, a place where emptiness and energy are so tightly mixed that the distinction between them blurs. As you let that image settle, it can be comforting to remember that everything around you, everything that feels firm, is held together by these hidden storms. The chair, the walls, your own body, all woven from protons and neutrons whose interiors we can never see directly, only infer from the quiet arcs of scattered particles. Each layer we have uncovered has brought us closer to the heart of matter, and at each layer, the universe has answered our questions with more subtlety than we expected. And somewhere just beyond the reach of our current tools, another question is already forming. If we could go even deeper, beyond the energies that reveal quarks and gluons, would the pattern grow wilder or simpler? Would the storm give way to something calmer or to a new kind of turbulence entirely? Once you start wondering that, it feels almost inevitable to ask, what happens if we keep going? If protons and neutrons are not solid, but storms of quarks and gluons, Is there some way to lean even closer to that storm? To disturb not just the particles themselves, but the deeper fields that give them their properties? That quiet desire is what led to one of the strangest machines humans have ever built. Not a telescope aimed at the sky, but a kind of inward-turning eye, buried in a loop under the gentle countryside along the French-Swiss border. From far above, nothing seems unusual. Fields, roads, small towns. But deep below runs a circular tunnel, about 27 kilometers around, where protons race in opposite directions, guided by invisible hands of magnetism. This is the Large Hadron Collider. People sometimes imagine it as a kind of weapon, a ring of wild, uncontrolled energy. In reality, it is more like a very large, very patient microscope. It has no glass lenses, no mirrors. Instead, it uses magnetic fields to hold and steer beams of protons that move so close to the speed of light that the difference hardly has meaning anymore. The goal is simple to say and almost impossible to do, to create collisions so energetic and so cleanly measured that we can glimpse the structures and fields that normally stay hidden inside the vacuum itself. Each proton in those beams is given an enormous amount of energy compared to its resting mass, about 7 trillion electron volts. That number can sound abstract, but you can think of it as how sharply we're sharpening our probe. One such beam goes one way, another goes the opposite way. When they meet head-on, the combined energy of the collision can reach about 14 trillion electron volts. That scale was not chosen at random. Calculations suggested that somewhere around there, the quiet background field that gives mass to many particles, the Higgs field, could be shaken hard enough to produce a tiny, fleeting ripple, the Higgs boson. When physicists say the collider sees the Higgs, they do not mean that it takes a picture of some glowing cloud. The Higgs field itself fills all of space, silent and invisible. What the LHC does is more like tapping the surface of a very still pond in just the right way. For an instant, a small wave appears, a particle, which then quickly breaks apart into other particles. By catching those fragments and tracing them backward, you can infer that the wave must have been there for a moment, even if you never saw it directly. The conditions that make that possible are extreme, but they last for almost no time at all. When two protons finally collide in the LHC, their energy is squeezed into a region smaller than the nucleus of an atom. For a heartbeat far shorter than any human can imagine, a trillionth of a second, the local vacuum is pushed into a different state. Particles appear and vanish. Energy becomes mass. Mass decays back into other forms. In that tiny flash, the world behaves the way it did when the universe was unimaginably young, less than a trillionth of a second after the Big Bang. The reason this machine is still, at its core, a microscope is the same rule that has guided us all along. Higher energy lets us explore smaller distances. Soft, visible light gave us cells and tissues. Faster electrons gave us atoms and crystal lattices. Beams of billions of electron volts revealed quarks inside protons. Now, with trillions of electron volts, we can nudge the fields that shape those quarks and give them mass. To make this happen, the engineering has to be as delicate as the physics is bold. Inside the tunnel, more than 1,000 large magnets bend and focus the proton beams. They must carry enormous currents without resistance, so they are cooled to about 1.9 Kelvin, colder than the average temperature of deep space. Around the circulating beams, the pipes are pumped almost completely empty. The vacuum is cleaner than the emptiness between stars. so that stray atoms will not bump into the protons and spoil their path. All of this effort is aimed at bringing those beams to cross in just a few chosen places, where enormous detectors wait. These detectors are not microscopes as we know them, but layers upon layers of sensors surrounding the collision point, like the shells of an onion. When protons meet and explode into showers of new particles, those particles pass through the detector, leaving tiny electrical traces. By collecting those traces and reconstructing them, physicists can rebuild what happened at the instant of impact. Among these instruments, two stand like quiet giants. They were the ones that first gathered enough evidence to confirm the Higgs boson. Out of more than 1 billion collisions every second, only a tiny fraction match the specific patterns expected when a Higgs is produced and then decays into other particles. Those patterns are faint, easily lost in the noise of more ordinary events. They exist for such a brief time that no single sensor ever sees a Higgs. What we have instead is statistics, a careful accumulation of many rare events, enough to say with confidence that a new particle with particular properties must have been there. When that evidence finally became strong enough, the moment itself was quiet and human. The physicist whose early work had predicted the Higgs field sat in the audience, listening to decades of theory and experiment come together. It was not just the discovery of a new particle, it was a sign that the framework we use to describe known particles and forces, the Standard Model, was, at least in one important way, on the right track. But this leads to another gentle question. Just how deep does such a machine really see? If we treat the LHC as a microscope, its maximum energy of about 14 trillion electron volts corresponds to a resolution of roughly 10 to the minus 19 meters, about 1/10 of a femtometer. That is smaller than the radius of a proton, pushing down toward the scale where quarks and gluons are tightly bound in their swirling confinement. At that level, we are not only counting particles, we are probing the fields themselves. The Higgs field, the electromagnetic field, the fields of the strong and weak nuclear forces. These are not things that sit inside space like objects on a table. In our best understanding, they are what space is doing. They are continuous presences, spread everywhere, that can be excited into particles. When the collider runs, it is not just smashing little beads together. It is shaking these fields and watching how they respond. For all its power, though, the LHC is still very far from the scale where gravity and quantum effects would merge in a violent way, the Planck scale. To reach that frontier directly with a similar machine, we would need energies, not trillions, but something like 10 billion trillion times larger. That would demand an accelerator on a scale we can hardly picture, perhaps as large as a galaxy, and materials and technologies far beyond anything we know. In that sense, the LHC is not the ultimate microscope, but a bridge, the sharpest tool we currently have, that reaches from the well-tested world of ordinary particles into the first hints of whatever may lie beyond. One of the most remarkable things about this bridge is that it does not simply observe what is already there. A traditional microscope relies on light reflecting from existing structures. The LHC does something more radical. By concentrating energy into a tiny region, it briefly recreates pieces of the universe's early history. It calls particles into existence that have not been around in free form since the cosmos was very young. Then, as they decay, it listens closely to what their behavior reveals. The amount of information produced in this process is staggering. Each collision throws out a pattern of tracks and flashes in the detectors. Specialized electronics decide in fractions of a second which events might be interesting and which can be safely discarded. The data that are kept are sent out across a global network of computers, a distributed system connecting institutes and universities in many countries. There, the events are sifted, categorized, and compared with the predictions of theory. Thousands of people are involved in this work. Engineers who keep the magnets cold and the beams stable, programmers who design the trigger systems, analysts who search for tiny deviations in enormous datasets. Quietly, day after day, their combined effort allows us to ask questions no single person could answer alone. There is something deeply gentle in that. The whole planet, in a sense, leaning together to listen to the smallest possible echoes. Since the first announcement of the Higgs, the collider has kept running, with pauses for upgrades and improvements. It has searched for signs of new symmetries, for heavier partners of known particles that might hint at a more unified underlying theory. It has looked for particles that could make up dark matter, for rare processes that occur only once in billions or trillions of decays. It has measured the strength of the strong force at energies far higher than before, tracing how quarks and gluons behave when the storm inside a proton is stirred intensely. So far, many of the hoped-for new particles have not appeared. The standard model has proven stubbornly accurate. Instead of dramatic cracks, we have found small tensions, subtle anomalies that might be hints or might simply be statistical flukes. In response, the collider is being prepared for even brighter running, with more collisions per second, sharper sensors, and more refined analyses. This high luminosity phase will not raise the maximum energy much, but it will greatly increase the number of chances we have to catch rare phenomena. Behind the technical details lies a simple, lingering feeling. We know that our picture of the universe is incomplete. We have evidence that most of the matter in the cosmos is dark, interacting hardly at all with the particles we know. We see that the expansion of the universe is speeding up in a way that suggests some form of dark energy. Gravity itself, described so elegantly by general relativity, still sits awkwardly beside the quantum fields of the standard model. The LHC lives in the space between what we understand and what we suspect. Perhaps, to uncover the next layer, we will one day need machines more powerful than this one, able to reach energies in the hundreds or thousands of trillions of electron volts. Perhaps the next threshold lies just beyond the LHC's reach. Or perhaps the clues are already hidden in the data we have, waiting for a new way of looking, a fresh idea about what to ask. For now, the collider stands as a kind of doorway, not an end of the story, but an opening into a region where our intuition starts to falter. It is an eye that looks with energy instead of light, letting us watch the universe replay, in tiny fragments, the moments when its basic ingredients first took form. And still, another question waits quietly at the edge of all this effort. If we keep raising the energy, keep focusing more and more into smaller and smaller regions, there will come a point where another law begins to stir, where gravity itself starts to notice what we are doing. What happens then, when our attempt to see more makes space-time lean back and answer? We've been following a simple rhythm so far. To see smaller, we need more energy. Each time we sharpen our vision, we push harder. We built microscopes of glass, then of electrons, then of particles flying just shy of light speed. It feels natural to think that if we just keep turning that dial, we can go on forever, peeling reality back layer by layer. But somewhere along that path, the universe begins to lean back. The quiet culprit is gravity, usually so gentle in our daily lives that we hardly notice it. It keeps our feet on the ground, holds planets in their orbits, shapes the slow turning of galaxies. Compared to the crackling intensity of nuclear forces or the buzzing of electrons, it seems almost lazy. And yet, when we try to look too closely, gravity becomes the one voice we can't ignore. The rule that guides us inward is straightforward. Finer details require shorter wavelengths, and shorter wavelengths demand higher energy. To resolve atoms, we fired electrons with hundreds of electron volts. To peek inside the nucleus, we used beams carrying billions. To disturb quarks and gluons, we reached trillions. Every step deeper means packing more energy into a smaller and smaller region of space. At first, this feels like nothing more than clever engineering. Build better accelerators, focus beams more tightly, improve detectors, but underneath the hardware lies a softer, more universal truth. According to Einstein, energy and mass are different faces of the same thing, and mass bends space-time. So whenever we concentrate energy, even in the name of curiosity, we also curve the fabric on which everything plays out. In most experiments, that curvature is unimaginably tiny. No one worries about gravity when using an electron microscope to look at a cell. Even in giant accelerators, for a long time, its influence is so weak it can be ignored. But as our probes grow more energetic, as the region we're trying to examine shrinks further, the energy density begins to climb into a realm where gravity is no longer just a quiet background. You can think of it like this. Every time we try to localize energy, to pin it down into a smaller and smaller volume, we make space-time itself more uneven in that spot. The greater the energy, the deeper the dimple we press into the fabric. At some point, that dimple becomes so steep that not even light can climb back out. That is the moment when looking too closely stops revealing and starts erasing. Physicists have a way to talk about this, using a simple idea. If you compress enough energy into a small enough space, that region behaves like an object with mass. And if that effective mass is concentrated within a certain critical radius, its gravity becomes strong enough to form what we call an event horizon, a boundary beyond which nothing can escape. That critical radius has a name, the Schwarzschild radius. For everyday objects, it is absurdly small, far smaller than the object itself, which is why we don't see them turning into black holes. But as you imagine concentrating more and more energy into a smaller and smaller sphere, the Schwarzschild radius grows, while the region you're probing shrinks. Eventually, the two scales meet. At that meeting point, something important happens. The target region you are trying to explore is now as small as its own gravitational radius. Any light or particles that try to leave are pulled back in. Your ultra-powerful probe, instead of tracing structures, has created a tiny black hole. Adding more energy no longer sharpens your picture. It just makes the black hole bigger. It's a kind of cosmic diminishing return, but far more final than the phrase suggests. From this interplay, a particular length falls out, the Planck length, about 1.6 times 10 to the power of negative 35 meters. It's a scale so tiny that normal language slips. If you took a proton and somehow enlarged it until it was as big as the Earth, the Planck length would still be smaller than a single atom on that enormous proton planet. It is many, many orders of magnitude beyond anything we can directly imagine. At roughly this length, the region you are trying to resolve is so small that the energy required to probe it has a gravitational radius of the same order. Any attempt to look closer, to pour in more energy, would only cause the region to collapse into a black hole. Nature doesn't let you focus more sharply than this. Not because our machines are weak, but because space-time itself refuses. Compare this with the energies we can actually reach. Protons in the Large Hadron Collider are pushed up to about 7 trillion electron volts. That lets us probe distances down to around 1/10 of a femtometer, smaller than a proton's radius, already a staggering achievement. To reach the Planck length, we'd need energies around 10 to the power of 19 giga-electron volts, a trillion times higher. In loose terms, it would be like concentrating more power than all the shining stars in the observable universe into a single microscopic point. So the universe wraps its smallest scales behind a gravitational curtain. The more intensely we try to illuminate that curtain, the tighter it draws. It's not that our technology fails. It's that the rules of the game themselves change. Sometimes this tension is described as a quiet duel between quantum mechanics and gravity. Quantum theory encourages us to localize, to measure, to sharpen. It tells us that by using shorter wavelengths, higher energies, we can pin down positions more accurately, at least in principle. But gravity replies, the more you concentrate that energy, the more violently space-time curves, until position stops being a meaningful word. At modest energies, quantum mechanics wins easily, and gravity is a distant whisper. At very large scales, planets, stars, galaxies, gravity dominates, and quantum effects can be brushed aside. At the Planck scale, though, neither can be ignored. The two great theories of the 20th century, which work so beautifully in their own realms, insist on speaking at once, in different languages, about the same place and time. That is where our current understanding falters. To get a feeling for how tiny this frontier really is, imagine starting from something already small, like a proton. You zoom in until the proton fills your view. That alone already spans a fantastic journey inward, from atoms, molecules, cells, and everyday objects. Now imagine going 1 trillion times further in. You are stepping toward the Planck scale, into a realm where space and time are thought to bubble and fluctuate like a restless surface, where the smoothness we take for granted breaks down. At that depth, the usual distinction between here and there, before and after, may blur. The lines we use to draw coordinates in space-time, those quiet grids that underpin our calculations, may no longer make sense. It's not just that we don't know what happens. Our current concepts are not built for such turbulence. Physicists sometimes call this boundary the black hole barrier. The idea is simple and a bit haunting. No matter what clever technique you try, if your experiment demands enough energy in a small enough volume to resolve distances beyond the Planck length, gravity steps in. A horizon forms. The very act of trying to see further causes the region to slip behind an invisible curtain. Your curiosity writes the conditions of its own limit. This isn't just a mathematical trick. The same logic explains why massive stars can turn into black holes. When a star much heavier than our sun exhausts its fuel, nothing is left to hold up its own weight. The core collapses, squeezing its mass into a smaller and smaller volume. Once that volume shrinks inside its Schwarzschild radius, light can no longer escape. The star's heart disappears from our view, hidden behind an event horizon. The process that sets the boundary in experiments is the same that defines the edge of a black hole. One physicist once described it this way: the closer you try to get to that gravitational boundary, the more violently the laws of physics resist your intrusion. That resistance, the intensifying curvature, the swelling of the horizon, is part of what defines the Planck scale. Nothing physical blocks your path. There's no wall or barrier in the usual sense. Instead, the geometry of space-time itself conspires to keep that region from being exposed. Seen from one angle, this is an act of protection, not hostility. If there were no such limit, we could imagine packing energy arbitrarily tightly, tearing the fabric of reality into something uncontrolled. Instead, gravity steps in and says, "This far." It prevents us and any process in nature from collapsing space-time into something undefined. It keeps energy, matter, and geometry in a kind of mutual balance. But the same protection leaves us with an unfinished tale. If we cannot look beyond this barrier with any probe we know how to build, how can we hope to understand what space-time is made of at its deepest level? Are we forever kept at arm's length from the ultimate texture of reality? Questions like that are what drive the search for a theory of quantum gravity, a framework that would weave together quantum mechanics and general relativity into a single, consistent story. Many ideas have been proposed. Some picture space-time as woven from tiny loops, forming networks that give rise to area and volume in discrete chunks. Others imagine that particles and forces are different vibrations of small strings, and that what we see as a point is really a blurred outcome of many possible oscillations. Each of these visions tries to answer the same gentle puzzle. What happens when space-time itself is as jittery and uncertain as the particles that move within it? How does the notion of a black hole barrier change when, at the smallest scales, positions and energies can never be pinned down exactly, only described by probabilities? We don't yet know the full answer. Our equations give us hints and approximations. Simpler models in fewer dimensions can be solved and studied. Thought experiments involving black holes and quantum information suggest that space-time might be more relational, more emergent than the stage we once imagined. But a complete, tested theory is still out of reach. In the meantime, we live with this delicate paradox. The more we try to sharpen our view of the foundations of the universe, the more those foundations bend away from us. The tighter we squeeze our beam of energy, the more we encourage space-time to fold into a shape that hides itself. And yet, this tension is part of what makes the universe stable enough for us to exist at all. The same interplay that blocks our experiments at the Planck scale also keeps atoms from collapsing under their own energies and keeps stars from turning instantly into singularities. It sets quiet boundaries that allow structures to form and persist. Near a black hole, time itself slows for an outside observer, stretching moments into long pauses as you approach the horizon. In an abstract way, something similar might happen at the Planck scale. Perhaps time and space do not end there, but the very idea of measuring their flow loses meaning. What it means for something to happen may change. Even so, this gravitational pushback is not the end of the story. It marks the beginning of one of the most intriguing frontiers in modern physics, the place where our best theories both succeed and fail at once. Because once we accept that space-time collapses under intense scrutiny, we are invited to ask an even softer, stranger question. What happens when we let quantum uncertainty share that burden? When the jitter of particles and the curve of geometry are allowed to play together fully, what new picture of reality might emerge? We've reached a place where gravity and quantum uncertainty are both speaking at once, each insisting on its own rules. From here, a natural question rises. Does this tug-of-war end somewhere? Is there a last step inward, a smallest zoom, beyond which the idea of distance itself begins to fade? Physicists give a quiet, careful name to that frontier, the Planck length. It's not just another small number on a long scale. It's meant to mark the point where the tools we use to describe reality, smooth space-time on one hand, jittery quantum rules on the other, stop working as separate stories. Below this scale, it isn't just that we haven't looked yet, it's that the way we think about space may no longer make sense. What makes the Planck length special is that it doesn't come from a lab measurement. No one has built a ruler that tiny. Instead, it falls out of pure reasoning, almost like a whisper between three constants that show up everywhere: the speed of light, which limits how fast anything can move; Newton's gravitational constant, which sets the strength of gravity; and Planck's constant, which measures how grainy quantum action is. If you take those three together and ask, what combination of them would give me a length, there is a unique answer. When you work it out, that answer is about 1.6 times 10 to the power of -35 meters. That is the Planck length. At that scale, the gravitational pull associated with a given packet of quantum energy is just strong enough to fold space-time in on itself. Quantum mechanics and gravity are no longer mild corrections to each other. They are equally fierce. Numbers this extreme are hard to feel, so it can help to walk down to them, step by step. A human hair is maybe 1/10 of a millimeter across. A red blood cell is a few thousand times smaller than that. An atom is another factor of 10,000 smaller. A proton inside the nucleus is still another 100,000 times smaller than the atom. Each step you imagine is a leap into a quieter, more microscopic world. Now take that proton and divide its size by 10 billion. Then do that again and again. Keep going, 30 times or so. Somewhere past those repeated divisions, you arrive at the Planck length. By then, you're so far inside the usual scales that words like small and tiny no longer have weight. You are comparing a raindrop to a galaxy again and again, and still not quite catching how extreme it is. At such scales, the picture of space-time as a smooth, calm stage begins to crumble. The neat grid lines we draw in our minds to mark out here and there are no longer reliable. Quantum uncertainty, which normally nudges particles and fields, now nudges geometry itself. Space and time begin to flicker, not just in what they contain, but in what they are. One way physicists talk about this is through an image called quantum foam. It's a way of saying, if you could somehow magnify the fabric of space-time down to the Planck scale, you might not see a flat sheet at all. You might see something seething and restless, tiny bursts of curvature flaring and fading, little tunnels and bubbles appearing for an instant and then vanishing. What looks like empty space at human scales could be down there, more like a boiling surface. To probe that storm directly, you would need energies beyond anything we can seriously imagine harnessing. The natural energy associated with the Planck scale is around 10 to the power of 19 giga-electron volts. The Large Hadron Collider, with all its quietly heroic complexity, reaches about 10 to the power of 4 giga-electron volts. That leaves a gap of 15 orders of magnitude, 1,000,000 billion times between what we can do and what would be needed. If you dreamt of building an accelerator big enough to reach that energy, simple estimates suggest it would stretch for thousands of light years, and that's before you reckon with the deeper problem. At such energies, the gravity created by the beams themselves would be so strong that the experiment would collapse into a black hole the moment it tried to run. The machine would never see its own data. The universe does not merely shrug at this idea, it forbids it. So the Planck scale is not just an engineering challenge, it's a limit of principle. Try to push a probe beyond it, and gravity responds by folding the region out of view. The act of trying to measure something smaller pulls a curtain across your view, and that curtain is geometry. What that curtain means is still an open question. Some scientists think of the Planck length as a kind of ultimate pixel size, a smallest unit of area and volume, the way a digital screen has a smallest dot. In that picture, you cannot talk about half a Planck length any more than you can talk about half of the smallest possible pixel. Other thinkers see the Planck scale less as a hard grain and more as a threshold, a smooth handover to a deeper description where space is no longer fundamental, but something that emerges from more basic ingredients. Either way, our current mathematics softly tells us the tools you use above this scale cannot be trusted below it, not because nature ends there, but because your language does. From the Planck length, you can also build another number, the Planck time, the shortest interval that can be meaningfully discussed in the same spirit. It is about 10 to the power of negative 44 seconds. Below that, the usual chain of cause and effect, this happens, then that starts to blur. It's not that nothing happens, it's that our way of marking before and after in such tiny durations may simply not apply. These scales are not just curiosities. Together, they frame the earliest era of the universe, a time we call the Planck era. It's the first, unimaginably brief sliver after whatever we mean by the Big Bang, when the universe was smaller than an atom, hotter than any furnace, and denser than any star. In that fleeting instant, all the forces we now treat as separate, the strong nuclear force, electromagnetism, gravity, are thought to have been tangled together. The Higgs field had not yet settled. Particles, fields, and geometry were part of the same churning whole. We do not see that time directly. The oldest light we can currently observe, the cosmic microwave background, comes from when the universe was about 300,000 years old, long after space had expanded, cooled, and become transparent enough for light to travel freely. By then, the Planck era was far in the past, a forgotten childhood. The Planck scale marks, in that sense, the edge of our cosmic memory. Beyond it, we rely not on observations, but on the hints left in the structures we see today and the consistency of our equations. Because our known theories fail there, many of the boldest ideas in modern physics are really attempts to step gently past that edge. String theory, for instance, suggests that what we think of as particles are actually tiny vibrating loops or segments of string with typical sizes on the order of the Planck length. In that picture, you never deal with perfectly sharp points, which are the source of many infinities in quantum field theory. The fuzziness is built in. Another approach, loop quantum gravity, starts from the geometry side instead. It imagines that space itself comes in discrete units, little quanta of area and volume, linked in an ever-changing network. Distances and surfaces are not continuous, but made from these interlocked building blocks, each carrying a small but non-zero chunk of geometry. Again, the characteristic size of these chunks is roughly set by the Planck length. The details of these theories differ and are still being tested, refined, and debated, but they share one quiet agreement. Below the Planck scale, the word distance stops behaving the way we expect. You cannot simply divide space into arbitrarily small pieces. At some point, the very act of trying to define closer loses meaning, like talking about half of a single note in a musical scale that has no finer subdivisions. In that sense, the Planck length is not a wall we can someday climb over with better technology. It's more like a horizon drawn by the nature of space and time themselves. On this side, our usual notions apply. Beyond it, the map must be redrawn with different ideas. There is a small irony woven into all of this. The Planck length is built from three constants: the speed of light, Planck's constant, and the gravitational constant, g. Two of them, c and h, are known with exquisite precision, measured so carefully that many definitions in physics now use them as fixed references. The third, g, is comparatively fuzzy. Gravity is weak and hard to measure on small scales, and our best determinations of its strength still carry more uncertainty than we would like. That means the numerical value of the most fundamental length we can write down depends on the one constant we understand least well. Even at the deepest theoretical boundary, there is a hint of incompleteness, a reminder that our knowledge is always a little rough around the edges. The idea of a minimal length doesn't just live in abstract theory either. It seeps into how we think about information and storage in the universe. There is a principle, born from the study of black holes, that suggests the amount of information that can be contained in a region of space is not proportional to its volume, as you might expect, but to the area of its boundary, measured in Planck-sized squares. In this view, each tiny patch of area, each Planck area, corresponds to about one basic bit of information. If this holographic way of thinking is right, then reality at its deepest level might be pixelated in a subtle way, with the pixels living not inside volumes, but on surfaces. When black holes radiate and slowly evaporate, the rate at which they lose information appears to be tied to these Planck-sized units of area. It's one of the first clear hints that any future theory of quantum gravity will have to treat information and geometry as deeply intertwined. So is the Planck length truly the final wall of reality, the smallest meaningful tick on the cosmic ruler, or is it just the first signpost of a deeper landscape, one that we haven't yet learned how to describe? For now, we don't know. What we can say is that every measurement we make, every theory we trust, rests on the assumption that space and time can be treated as smooth and continuous, at least on scales larger than this tiny frontier. If, instead, they are built from discrete, Planck-sized building blocks, then everything we see, every smooth curve, every continuous motion, is an approximation, like a detailed image, seen from far enough away that its pixels blend together. Some physicists like to say that at the Planck scale, space is not a calm backdrop at all, but an active participant, a weave of quanta whose patterns give rise to the distances, durations, and paths we experience. If that's true, then the Planck length is less a brick of reality and more a clue to how the weave is stitched. And if this length really does mark the last meaningful step of smaller, another question comes softly into view. The uncertainty principle, which tells us how sharply we can know positions and momenta in ordinary quantum mechanics, was written without gravity's voice in the room. But if there is a built-in minimum distance, if trying to localize things too much summons space-time's own resistance, then perhaps that principle itself must bend. What does uncertainty look like when gravity joins the conversation? We've been circling around a quiet idea for a while now, that there might be a smallest, meaningful step in space, a finest tick on the ruler of reality. But there's another principle, born long before anyone spoke of Planck lengths or quantum foam, that brushes against this same frontier from a different side. It begins with the simple act of asking where something is. In the early days of quantum theory, Werner Heisenberg realized that at very small scales, nature refuses to let us pin things down too neatly. If you try to measure a particle's position very precisely, its momentum, how fast and in which direction it's moving, becomes uncertain. And if you measure its momentum carefully, its position spreads out into a blur. It's not that our microscopes shake or that our hands are clumsy. Even in a perfectly quiet lab with flawless equipment, the uncertainty remains. It's as though reality, at its most delicate, tucks its exact coordinates behind a soft curtain of probability. Heisenberg wrote this limit into a simple relation between the uncertainty in position and the uncertainty in momentum. The smaller one becomes, the larger the other must be. There's always a trade. That relation has guided generations of physicists, shaping the way we think about electrons in atoms, light in cavities, even vibrations in crystals. But there was an unspoken assumption sitting in the background. The stage itself, space-time, was fixed and calm. The geometry did not respond to the act of looking. Once gravity enters the conversation, that calmness starts to fade. Imagine, gently, that you're trying to locate an electron in space. You shine light on it, a photon with a certain wavelength. If the wavelength is long, like radio waves or warm infrared, the light can't distinguish small details. It washes over the region, telling you only roughly where the electron might be. So you reach for shorter wavelengths, higher energy photons, because shorter waves can, in principle, resolve finer structures. This is exactly the logic that built microscopes and particle colliders. But now remember, each photon carries energy, and energy bends space-time, even if only a little. At first, with modest energies, that bending is ridiculously small. You can ignore it. Yet if you keep going, picking higher and higher energy photons to sharpen your view, the energy you focus into that tiny region grows. The photon you're using as a probe starts to have its own noticeable gravitational field. Suddenly, the act of measurement is no longer a gentle touch. The photon you send in to reveal the electron's position also distorts the geometry around it. The very coordinates you're trying to define are being tugged and warped by the energy you use to measure them. Push this thought experiment far enough, and something more dramatic happens. There comes a point where the energy of that single photon, squeezed into the tiny volume where you're trying to localize the electron, would be enough to create a minuscule gravitational well, a tiny black hole forming right at the site of your measurement. Instead of getting a sharper picture, the region vanishes behind an event horizon. The question, where is it, dissolves into somewhere inside that invisible boundary, and the experiment has lost the very thing it set out to gain. Out of this kind of reasoning grows what many physicists call the generalized uncertainty principle. It takes Heisenberg's original idea that position and momentum cannot both be arbitrarily precise and lets gravity add its own quiet correction. At low energies, where gravitational effects are negligible, the usual quantum behavior dominates. The more precisely you know a particle's momentum, the more its position smears, and vice versa. But as you increase the energy of your probe, and therefore the strength of its gravitational influence, something new appears in the balance. The uncertainty in position no longer shrinks without limit as you push harder. It shrinks and then reaches a minimum. Beyond that, adding more energy makes your effective position uncertainty grow again. In other words, if you include gravity, there is a smallest blur. You can't squeeze the uncertainty in position below a certain scale, no matter how clever or determined you are. Trying harder only stirs space-time more violently and makes things less clear. That smallest blur lines up with the Planck length, the same tiny scale that appeared when we combined the speed of light, the strength of gravity, and the grain of quantum action. It arrives here not from telescopes or colliders, but from a quiet thought experiment about measurement itself, how light, gravity, and quantum uncertainty weave together when you insist on knowing exactly where something is. There is a certain gentle beauty in that. On one side, Heisenberg's principle tells us that exactness in the quantum world is always shared between partners, position and momentum, time and energy. On another, Einstein's relativity tells us that energy and mass curve the fabric of space-time. The generalized uncertainty principle is the place where those truths meet, not in a forced way, but almost inevitably. It suggests that even if we never build machines anywhere near the Planck energy, the universe has already written a safeguard into its structure. The geometry itself will not allow us to pack information into regions smaller than that fundamental scale. Ideas like this have echoed through several attempts to describe quantum gravity more fully. In string theory, the basic objects are not point-like particles, but tiny loops or segments of string. When you pump energy into a string, trying to localize it more, it doesn't simply shrink, it also vibrates more intensely, and those vibrations tend to stretch it out. Past a certain point, the more energy you add, the larger and more extended the string becomes. What began as an attempt to focus turns into a spreading. The theory itself resists being compressed below roughly the Planck length. In loop quantum gravity, the emphasis shifts to space itself. Areas and volumes are not continuous, but come in discrete chunks, a kind of geometric spectrum. These chunks are incredibly small once again, on the order of the Planck scale. You can have 1 unit of area, or 2, or none, but not half of the smallest non-zero amount. Below that, distance simply isn't defined in the way we usually mean it. Even though these approaches are very different in spirit, they keep arriving at a similar refrain. There is a minimum meaningful scale, a built-in softness to the notion of here that no probe can pierce. The fingerprints of this idea show up in places that, at first glance, seem far removed from thought experiments with a single photon. When Stephen Hawking worked out that black holes must slowly radiate and lose mass, he found that a black hole's temperature and the amount of information it can contain are closely tied to its surface area, measured in Planck-sized units, not its volume, but its area. It was as if the horizon itself, its two-dimensional skin, held the bookkeeping for all the information hidden within. From that insight grew a broader suggestion, often called the holographic principle. The amount of information that can be stored in a region of space is proportional not to how much space there is inside, but to the area of its boundary in Planck units. Each tiny patch of area, each Planck square, corresponds to roughly 1 bit of information. Space, in this view, is less like a 3-dimensional box filled with data, and more like a screen whose pixels live on its edges. If you think of the generalized uncertainty principle alongside this, a picture quietly forms. There is a smallest spatial fuzziness set by the Planck length. There is a smallest meaningful tick of time set by the Planck time. There is a maximum density of information tied to areas measured in these tiny squares. Together, they suggest that knowledge itself has a natural grain not imposed from outside, but arising from the way quantum behavior and gravity weave the world. A simple thought experiment helps to feel this strangeness. Imagine trying to measure the position of a particle more and more precisely. You build better detectors, Use shorter wavelengths of light. Push the energy of your photons higher and higher. At first, your accuracy indeed improves. The particle's wave function becomes more localized. But as you continue, the gravitational pull of each probing photon starts to matter. Its presence slightly deflects the particle, slightly warps the space-time you're using as your coordinate system. Keep going, and those distortions grow. At some point, the very act of sending a photon into that region introduces more uncertainty than it removes. Push beyond that, and your photon would, in principle, create an event horizon enclosing the particle. The question, where is it, has summoned a little patch of space-time that refuses to answer. On cosmic scales, telescopes like James Webb watch light stretch and redden as it travels through an expanding universe, tracing the large-scale shape and history of space-time. On the opposite extreme, these quantum gravitational thought experiments stretch the rules in a different direction, asking how far you can tighten a measurement before the concepts you're using begin to fold. Both types of exploration, one with delicate mirrors and cold detectors, the other with chalk on a board and equations on a screen circle, the same underlying issue. How finely can the universe be resolved before the notion of resolution itself becomes fuzzy? The generalized uncertainty principle does not present this limit as a hard brick wall, but as a region of deep blur. As you approach, position and momentum both resist being pinned down in the usual way. They trade clarity back and forth, and beyond a certain point, the exchange itself breaks the picture we started with. The universe, at that edge, is neither fully continuous nor neatly discrete. It is something in between. Heisenberg could not have known, when he first wrote about electrons and gamma rays, that his uncertainty principle would one day be extended into the realm of black holes and holographic screens. Yet the same soft refusal to be perfectly known that he described in the behavior of particles now seems to touch the fabric of space-time as well. As one physicist put it, quantum theory may not really be about things at all, but about relationships, how systems influence each other, how measurements connect observer and observed. When gravity joins that web of relationships, uncertainty ceases to be just a blur in our knowledge. It becomes part of how the universe holds itself together. And once you accept that there is a smallest meaningful distance you can probe, another gentle question follows close behind. If we can no longer think of matter as tiny points placed on a perfectly smooth background, if space itself may come in quanta, and the waves of matter refuse to be crammed into anything sharper than a Planck-length packet, perhaps the basic ingredients of reality are not points at all, but something more extended, shapes, loops, or patterns, whose very form is what gives rise to the space they inhabit. We've been slowly letting go of the idea that reality is made of perfect dots on a perfect grid. First, quantum mechanics softened the dots into waves of possibility. Then gravity reminded us that the grid itself can bend and fold. Somewhere between those two reminders, another thought began to take shape. What if the basic things aren't points at all? For much of the 20th century, the simplest picture of matter treated elementary particles as zero-size specks. An electron was a point. A quark was a point. Everything was built from these idealized dots. No width, no length, no inner structure, just position, charge, and a few other labels. For most purposes, that picture worked astonishingly well. It let us build transistors, lasers, GPS systems, and all the technologies that quietly hold up our days. But as physicists pushed their equations toward the Planck scale, toward energies and distances where gravity and quantum effects are equally fierce, those same equations started to crack. When two point-like particles collide at unimaginably high energies, the math tries to concentrate all that energy into an infinitely small region. The result is not a neat prediction, but a blow-up. Quantities racing off to infinity, curves in space-time becoming infinitely sharp. It's as if the theory is trying to tell us that asking what happens in exactly zero volume is asking the wrong question. So a new picture was proposed, gentle in its simplicity and wild in its consequences. Instead of dots, imagine tiny filaments, one-dimensional strands, so small that their natural length is close to the Planck scale. These strands can be open, like tiny line segments, or closed into loops. They do not sit still, they vibrate. In this view, what we call a particle is just one particular pattern of vibration on a string. Change the way the string vibrates, and you change the particle it appears to be. One mode feels like an electron, another like a photon, another like a quark. The different notes of the string become the different particles in the zoo of the standard model. This simple shift from points to strings does something extraordinary to those infinite spikes in the equations. Because a string has length, the energy in a collision is spread along that length. It cannot be squeezed into a perfect mathematical point. The harsh infinities that once plagued attempts to combine gravity with quantum mechanics begin to smooth out. Instead of space-time collapsing into nonsensical infinities whenever gravity is quantized, the theory stays finite, calm, well-behaved. Even more surprising, gravity itself is no longer an awkward extra you have to bolt on. When theorists let strings vibrate in every allowed way and wrote down how they interact, one particular vibration mode behaved exactly like a graviton, the hypothetical quantum of the gravitational field. In other words, the gentle curvature Einstein described appears as just one of the many possible patterns in the string's motion. Gravity falls out of the framework, not as an afterthought, but as a natural harmony. At lower energies, where our experiments live, the strings are so tiny and their vibrations so restrained that they look like ordinary particles. To microscopes and colliders, they may as well be point-like. That is why our older theories work so well in most situations. But as you imagine pumping more and more energy into them, as you try to zoom in harder, their behavior changes. Instead of revealing ever sharper substructure, the string's vibration becomes more excited, sprouting richer modes, spreading the energy along its length. The more fiercely you try to localize it, the more it resists being localized. In that sense, string theory quietly builds the generalized uncertainty we talked about into the matter itself. There is a minimal smear, set by the string's own length, below which it simply does not make sense to talk about sharper positions. You cannot compress a string beyond its fundamental scale. Add energy, and you do not make it smaller, you make it more active. It stretches in the space of possibilities, not in the space of coordinates. That is why, in this picture, infinite resolution stops being meaningful. There is a smallest useful zoom level, roughly at the Planck length, where the word distance is still coherent. Below that, extra energy does not carve nature into finer and finer pieces. It just excites new vibrations, new resonances, new ways for the same underlying object to move. The story of how this idea emerged has its own gentle twists. String theory didn't begin as a grand unifying scheme. In the late 1960s, it was introduced as a way to model the strong nuclear force, the force that holds quarks together inside protons and neutrons. The scattering patterns seen in early particle experiments could be described elegantly by imagining tiny strings whose vibrations matched the observed energy levels. Then came a surprise. Hidden among the allowed vibration modes was one that behaved exactly like a massless spin 2 particle, the signature of a graviton. Suddenly, this modest model of one force revealed that it naturally contained gravity as well. It was as if you tuned a small instrument to play a single song and found that, somehow, it held the harmonies of an entire orchestra. From there, the picture widened. If strings could give rise to the strong force and gravity, perhaps they could also accommodate the electromagnetic force and the weak nuclear force. Indeed, as the theory grew, it showed room for all of them. Different vibrational states correspond to different particles: photons, gluons, W and Z bosons, even the Higgs. Not just as separate pieces thrown together, but as expressions of one object moving in many ways. To make all of this consistent, the mathematics quietly asked for more room than we see. Instead of 3 dimensions of space and 1 of time, the natural setting for many string models involves 10 dimensions, or even 11 in some extensions. The extra dimensions are not wide and open like the ones we move through. They are thought to be curled up, compact and small, woven into shapes so tiny that no current experiment can probe them. The exact way those hidden dimensions are folded determines how strings can vibrate. And because the vibrations give us the particles and forces, the geometry of those compact spaces fixes the laws of physics that emerge. The shapes themselves, intricate, curved objects known by names like Calabi-Yau manifolds, are far beyond anything we can picture intuitively, but their role is gently simple. They are the silent molds that shape the possible music. There may be an enormous number of such shapes, each one corresponding to a different possible universe, each with its own spectrum of particles and constants. Faced with that landscape, it is easy to feel both awe and vertigo. But beneath the complexity, the same core idea holds steady. When you replace points with strings, the wild infinities of ultra-zoomed collisions soften. The smallest scales stop being a threat where space-time shatters and become a place where space-time hums. In this view, singularities, the infinitely sharp points that appear in classical descriptions of black holes or the Big Bang, are not literal tears in reality. They are places where our point-particle approximations break down. If we retell those stories in terms of strings, the blow-ups may be smoothed away. The energy that would have tried to cram itself into an exact mathematical point instead spreads along tiny loops, keeping curvature large but finite. Space and time bend deeply, but do not rip. All of this offers a kind of quiet reassurance. It suggests that the universe may have a built-in gentleness at its most extreme magnifications. Instead of letting our curiosity drive us toward edges where everything diverges, it arranges its ingredients so that, at the deepest level, the picture softens into structure rather than exploding into nonsense. We should also admit, softly, that string theory is still a work of imagination anchored to mathematics. The strings it speaks of are far beyond direct reach. No accelerator we can build in any near future will be able to resolve them. Evidence, if it comes, may be indirect, subtle imprints in the early universe's light, tiny deviations in particle behavior, or patterns that only make sense when seen as shadows cast by a higher dimensional geometry. For now, string theory stands as a beautifully consistent framework, a way to let gravity and quantum mechanics share the same stage without shouting each other down. It gives us a world where the smallest meaningful distance is not a violent boundary, but the natural scale of a gentle object, a tiny vibrating strand whose length sets the finest thread in the weave of reality. And yet, strings are not the only path people have followed into this deep quiet. Some physicists have taken a different approach, starting not from extended objects moving in a smooth spacetime, but from the idea that space itself might be built from discrete bits, tiny quanta of area and volume, stitched together by the spin of geometry. We've been following one possible picture of the deep world, not dots on a grid, but tiny strings, vibrating in ways that give rise to particles and forces. There is another way to tell the story, just as gentle, but starting from a different place. Instead of asking what the basic objects are, it asks a quieter question. What if the stage itself is made of quanta? Einstein taught us to think of gravity not as an invisible pull, but as the curvature of spacetime. Mass and energy bend the geometry. Planets follow those curves, light arcs along them. In his equations, spacetime is smooth, like a continuous fabric you can stretch and fold. That picture has carried us through a century of discoveries, from black holes to the expansion of the universe. But as we keep reminding ourselves, when we drift down toward the Planck length, that calm surface can't stay calm forever. Quantum fluctuations, which normally nudge particles and fields, begin to nudge geometry too. At those scales, the notion of a perfectly smooth fabric starts to look like an illusion born of distance. Loop quantum gravity takes that hint seriously. It doesn't introduce new kinds of matter, and it doesn't add extra dimensions. Instead, it takes Einstein's own idea that gravity is geometry and asks what happens when that geometry itself is treated as quantum. If light comes in packets, if energy levels in atoms come in steps, why should space be any different? In this picture, space is not a continuous expanse you can subdivide without end. It is quantized. There is a smallest meaningful chunk of area, a smallest meaningful chunk of volume, both on the order of the Planck scale. You cannot have half of that minimal volume any more than you can have half of a single photon of a given frequency. You can have none, or one, or many, but not less than one. To describe this, loop quantum gravity uses something called a spin network. You can imagine it, very loosely, as a web of nodes and links. Each node in the web carries a little packet of volume. Each link between nodes carries a little packet of area. Together, these quanta form a kind of microscopic scaffolding for space. From far away, that web dissolves into smoothness, just as a beach looks like a continuous stretch of sand until you bring a handful close to your eyes. The spin network looks like smooth space-time when you zoom out far enough. The curvature and dynamics that Einstein wrote down emerge as the averaged behavior of countless tiny loops and links. Up close, though, the continuity breaks into grains. You can think of these loops as closed lines of gravitational field, little circuits that carry the spin of geometry. The way they connect, twist, and knot together determines the shape of space at the smallest scale. Time, in this view, is not a perfectly flowing river either. It advances in tiny jumps, in discrete updates of the network, like a quantum clock gently ticking. One of the theorists who helped shape this view likes to say, simply, that at the Planck scale, space is made of grains, and the world is woven from loops of gravity. It's an image that sounds poetic, but underneath it lies the careful machinery of equations. When the gravitational field is written in the right variables and quantized, The mathematics naturally produces discrete spectra for area and volume. There are allowed values and forbidden gaps, just as in the energy levels of an electron orbiting a nucleus. Even empty space is no longer truly empty. It becomes a quiet structure, this web of quantum geometry that underlies everything else. Matter, fields, light, and motion all take place on a stage that has its own fine-grained texture. When we go back to larger scales, our familiar world returns. The network averages into smooth curves. Einstein's general relativity reappears as an effective description, the way a continuous fluid description of water emerges from countless molecules in motion. We don't throw away the older theory. We understand where it comes from. This has profound consequences for places where classical relativity runs into trouble. In the usual equations, if you follow a massive star as it collapses or trace the universe back in time toward the Big Bang, you eventually hit singularities points, where densities become infinite and the curvature of space-time blows up. Those infinities aren't so much physical predictions as they are signposts saying, the theory has been pushed beyond its domain. In loop quantum gravity, the granular structure of space refuses to let singularities form. You cannot compress a region smaller than 1 quantum of volume. When you try, the equations change. The geometry pushes back. Applied to the early universe, this leads to a different picture. Instead of a beginning from precise nothing, there is a minimum size, a densest state, allowed by the quantum geometry. Before that, according to some solutions of the theory, there may have been a contracting phase, a prior cosmos that shrank, reached that minimum, and then bounced into expansion. The Big Bang becomes a big bounce, a transition rather than a sharp birth. We don't yet know if this is how our universe actually behaved, but it's a gentle example of what quantized spacetime can do. It softens the extremes. Similar reasoning has been explored for black holes. In classical relativity, once you cross the horizon and head inward, all paths lead inevitably to a singularity. In a loop quantized geometry, the core might be replaced by a region of extremely high but finite density, where the network of loops reaches its tightest possible configuration and then, perhaps, evolves into something else. The exact story is still being worked out, but the key idea is the same. Quantum grains prevent infinite collapse. Because the Planck scale is so small, we cannot hope to look directly at this scaffolding with any microscope we can build. Instead, physicists look for faint hints that such a lattice might leave in the way light and particles travel across vast distances. If space-time has a subtle granularity, then, in some models, photons of different energies might not move in exactly the same way. Over billions of light years, a tiny difference in how they feel the underlying texture could add up to a small delay or distortion. High-energy gamma rays from distant explosions or delicate patterns in the polarization of ancient cosmic light might carry such fingerprints. Satellites and observatories have been watching the skies for these signs. So far, space-time looks remarkably smooth, even at the limits of our measurement. That doesn't rule out a granular structure. It just tells us that if it exists, its effects are gentler than our current tools can resolve. The search continues, inching closer with each improvement in sensitivity. In the broader landscape of ideas, loop quantum gravity sits as a kind of quiet counterpoint to string theory. Where strings introduce new fundamental objects and often extra dimensions, loops start with the geometry we already know and quantize it directly. Strings say, the music is in the vibrations of underlying filaments. Loops say the music is in the network of relationships that is space. Both perspectives, in their own ways, whisper the same underlying message. There is no such thing as a truly empty passive void. At the Planck scale, the universe is all structure, whether that structure appears to us as vibrating strings in a higher dimensional space or as a web of discrete quanta of area and volume. This changes how we imagine the cosmos at a deep emotional level too. Instead of a static stage on which matter moves, we begin to see a living network. Matter and geometry are intertwined. The presence of energy reshapes the pattern of loops. The pattern of loops guides where matter can go. The where and the what are no longer cleanly separable. If you could somehow zoom all the way down to the finest threads, you wouldn't find tiny marbles sitting in a vast black emptiness. You'd find the emptiness itself replaced by relationships, nodes connected to nodes, spins connected to spins, a web in constant, quiet motion. Seen from afar, that web becomes the familiar geometry of space and time. And once we start thinking in terms of networks and relationships, another question naturally rises through the calm. If the loops and links beneath space-time are what matter and geometry are built from, perhaps beneath them lies something more abstract still. Something that doesn't look like space or time at all, but like pure information patterns of correlation, out of which even the notion of a where and a when slowly emerge. We've wandered down to a place where even space and time feel a little uncertain, where strings, loops, and quantum relationships sit beneath the smoothness we live inside every day. There's one last quiet question to rest with. If distance itself is only an approximation, what can we still hope to measure? For centuries, how far and how long have been the main ways we describe reality. From Galileo timing falling bodies with his pulse, to spacecraft navigating by tiny shifts in starlight, distance and time have been our most trusted coordinates. We've stretched rulers outward with telescopes and inward with microscopes and colliders. It's easy to assume that, with enough cleverness, we could keep refining those measurements forever. But as we've seen, nature has drawn a soft boundary, and two very different paths lead us to it. One path starts with gravity. Einstein showed that energy and mass curve spacetime. If you pour enough energy into a small enough region, the curvature becomes so steep that light can no longer climb out. A horizon forms. The region turns into a black hole. Now imagine using ever higher energies to probe ever smaller distances. At first, this sharpens your view, but beyond a certain point, the energy you've packed into your measurement volume would itself be enough to trigger collapse. The experiment you built to reveal a tiny region would instead hide it behind a horizon. The act of looking too closely causes the scene to vanish. The other path begins with quantum uncertainty. Heisenberg taught us that position and momentum cannot both be known exactly. The tighter you try to pin down where something is, the wider its possible motions become. This isn't about clumsy tools. It's baked into the way the quantum world behaves. Normally, we imagine this playing out on a fixed stage, where space-time itself is unaffected. But once we remember that every photon we use as a probe carries energy, and that energy bends space-time, that quiet trade-off changes. Use a low-energy photon, and its wavelength is long. You can only localize your particle loosely. Use a higher-energy photon, and the wavelength shrinks, so you can, in principle, resolve finer structure. Keep going, and you reach a point where the photon's own gravity starts to deform the region you're trying to measure. Push harder still, and the curvature you create blurs the very position you hope to sharpen. In the end, If you insist on more and more energy, you don't get more precision. You get a tiny black hole. From this reasoning grows the generalized uncertainty principle. Below a certain scale, the uncertainty in position refuses to become smaller. It reaches a minimum about 1 Planck length, 1.6 times 10 to the minus 35 meters, and no clever trick can push past it. It's not that we lack a good enough microscope. It's that space-time itself no longer offers distinct points to label. Two different arguments, one from gravity's tendency to collapse, one from quantum theory's built-in fuzziness, lean toward the same quiet conclusion. At the Planck scale, the usual picture of distance and time dissolves. The smooth geometry Einstein described and the probabilistic waves of quantum mechanics stop being separate stories. They meet, clash, and hint that both are approximations of something deeper. Much of modern theoretical physics is an attempt to listen to that hint. String theory answers by replacing point particles with tiny vibrating filaments. At ordinary energies, they appear point-like, but when you try to probe them more sharply, they respond by stretching and sprouting new modes of vibration. The more energy you add, the less they resemble sharp dots, and the more they behave like extended musical objects. They refuse to live at a single exact point. Their own length sets a natural limit to localization. Loop quantum gravity starts from geometry instead. It says, if light and energy are quantized, perhaps space is too. In that picture, there is a smallest quantum of area, a smallest quantum of volume. Space-time becomes a web of relationships, nodes, and links in a spin network that only looks smooth when you're far enough away. Try to squeeze volume into less than 1 quantum, and the equations push back. A singularity never quite forms. Despite their differences, both pictures point toward the same gentle idea. Space and time might not be fundamental ingredients, but emergent ones. Like temperature emerging from countless molecules in motion, geometry might emerge from something more fine-grained. Vibrations of strings, loops of gravity, patterns of entanglement only becoming the continuous stage we know when many microscopic events blur together. On human scales, this emergent spacetime works beautifully. GPS satellites correct for relativistic time dilation and guide planes and ships with meter-level accuracy. Telescopes track the bending of light around galaxies. Spacecraft navigate through the solar system, following paths predicted by Einstein's equations and quantum field calculations. For galaxies, oceans, cities, and atoms, distance and time are as real as anything we know. But if you carry those same coordinates all the way down toward the Planck length, they begin to lose their grip. Rulers stop having meaning. Clocks stop having a clear tick. At those depths, what we can describe may no longer be where something is and when something happens, but how strongly it is entangled with something else, how information flows, how relationships knit together. Some ideas in quantum gravity lean into this wholeheartedly. They suggest that space itself might emerge from quantum connections. The more two regions of the universe are entangled, sharing information in subtle, non-local ways, the closer they behave to being in space. Distance, in that view, is not a fundamental property, but a measure of how tightly systems are woven together by their shared quantum state. No entanglement, no between. It's a disorienting thought at first, that reality might be built less from things in places and more from relationships and patterns of information. The universe becomes less a container and more a process, less a map of points and more a network of interactions. These ideas are still being tested, refined, and debated. They live at the edge of what we can currently measure. Future observatories may help us listen more closely. Space-based detectors, listening for gravitational waves, whispering across billions of light years. Precision instruments, measuring tiny deviations in how those waves spread. New maps of the cosmic background light that might carry scars from quantum geometry in the early universe. If, someday, we see small departures from the smooth predictions of relativity, tiny delays, subtle distortions, patterns that only make sense if space-time has a quantum texture, we might finally glimpse the fingerprints of that deeper layer. Even if that day is distant, one truth already rests quietly in our hands. There is a natural boundary to how sharply we can interrogate the world. The closer we look, beyond a certain point, the less the old language applies. Measurement stops being about finer marks on a ruler and begins to bump against the limits of what distance and time can mean. That isn't the universe slamming a door. It's more like a gentle nudge, turning us from trying to carve reality into smaller and smaller pieces toward trying to understand the patterns that hold it together. When we meet that boundary, physics doesn't have to end. It can shift from measuring to interpreting, from drawing maps to understanding the rules that make any map possible. We move from asking, "Where exactly is this?" to "How are these things connected?" From "How far?" to "In what way?" In that shift, the cosmos doesn't become smaller or more inaccessible. In a quiet way, it becomes richer. The familiar notions of here and there, before and after, reveal themselves as layers, useful, beautiful, but not final. Beneath them, something more abstract and more subtle may be at work. Information, relationships, patterns of entanglement from which space, time, and matter all slowly arise. If this slow journey into the very small has kept you company tonight, if it's eased your thoughts or given you a softer way to hold the mystery, I'm really grateful you stayed. If you feel like leaving a gentle like or a soft tap on subscribe, it helps these quiet stories find others who might need them too. And if you'd like to share, I'd love to know where in the world you're listening from this evening. Your presence here is like a small light in the dark, one point of awareness in a vast, unfolding universe. Thank you for drifting through these questions with me. Rest well, and may your dreams wander kindly through the spaces between the stars.